Welcome back to Personal Technology Security. Today we'll discuss the ICS computational stack, and we'll move from the hardware level all the way up to the software, and more specifically we'll start at the lowest level, the programmable logic controller. That's the device that is the hardware device that controls the process, as we've seen in the previous lecture. And then on top of that we have the real-time OS that executes and interfaces with the hardware. And on the OS, on the real-time OS, we have the control software that is responsible for reading the input from the sensors, computing and actuating, and then the PLC, the hardware, the whole system is interfacing with other PLCs or with the central monitor system through specific industrial protocols. So today we'll see each one of them, each one of these layers, one by one, and we'll start by the lower level, the hardware level, the programmable logic controller. So what is a PLC? A PLC is like a computer. It's a computer it's more of a special computer. It's a hardened computer that has been adapted to withstand more hardship, for example, extreme temperatures, electromagnetic interference, and similar things that are more essential in a manufacturing process. PLCs can be something that's very small, that has a few inputs and a few outputs, or can be something very big. We still use a term PLC to capture both. So it can be something that it's a small PLC with just an input and an output sensor and actuator. It can be a huge rack that has many PLCs connected to each other network, or the PLC connected to a centralized SCADA system. And as we saw, compared to DCS and SCADA, PLCs can be a primary controller in a control system configuration. So SCADA systems were more event-driven, where you had some kind of data coming from different parts of your system, and then whenever there was an event, some action would be taken. A PLC is more a closed-loop environment, that it is the control loop we discussed before, we'll see more today, and it reads an input, it computes, it actuates, the actuation propagates to the process, and then there's a sensor again that provides an input, compute, actuation, and so on and so forth. So the hardware level, the PLC, as you can see from the table here, it has several vendors, have their own models, but then we start seeing the operating system, the architecture, to be mostly commercial off-the-shelf. So there has been a trend towards moving out of proprietary hardware and software towards commercial off-the-shelf hardware and software. And this table here shows that some of these examples would have ARM CPUs, x86 CPUs, or MIPS that are more commodity hardware. And the operating system, we see many of them supporting Linux, for example, or Windows operating systems. The good thing about commercial off-the-shelf hardware and software is that they're easy to program. There's an ecosystem that's been mature for years. You have your dedicated toolchains, compilers, GCC, that are it's easy to maintain and upgrade, right? Because you follow whatever the community is doing. You have your Linux kernel. There's a new version that has an improved GCC, so you can take it and incorporate it into your system. So having commercial off-the-shelf hardware and software allows you to easily program, maintain, and upgrade your system. On the negative side, whatever vulnerability shows up on these architectures, on the hardware and software, can be inherited to your control systems. And we saw that before when we were discussing the difference between IT and OT and the convergence between the two. The good side, easy to program, maintain, upgrade. The bad side, security vulnerabilities are not applicable in the OT world. And the last thing that's both a curse and a blessing is that since these are part of a community, if there's a security vulnerability, it will be patched. There will be a patch at some point that will be fixing whatever problem appeared in the hardware or the software. So that's the good thing. The bad thing is that this is a frequent occurrence nowadays. And frequent occurrence of patches is not very ideal for the OT environment, because as we saw before, in the OT world, you cannot just stop the system, upgrade it, and then put it back. You may need days or months to be able to stop it in a proper way and then replace or upgrade the PLC. So the fact that the security updates are available frequently is both good and bad. and probably you need a complementary solution to be able to, in the window that your system is unpatched, you have to do non-intrusive methodologies to ensure that your system won't be affected by the vulnerability. So this is the hardware side. Moving on, so that's the PLC. On the PLC, in the past there would be some kind of a monolithic firmware. Nowadays we see a transition to real-time operating system. And to explain that, we have first to understand what real-time means. So a system is real-time if the correctness of the operation is not only the logical correctness. It's not only I type something on the command line and I expect some response back, or I open Windows, PowerPoint, Word, and I get the software in front of me and I do some operation on it. It's not only the logical correctness, but it's also the time in which the operation is performed. So it's not only I open the Word, Microsoft Word, and it opens, it also has to open within 5 milliseconds. And if that doesn't happen, then my system is incorrect. So it's not only functionality, but it's also timing that is very important. And we can see two different types of real-time system. One is hard real-time. That means that once you pass a deadline, then it's useless. You can't do anything about it. You have to absorb the fact that you didn't respond in time, and this may lead to a critical failure or destruction of the system. So hard real time means completion within the deadline is very critical. Soft real time, on the other hand, means the completion is more of a quality of a service quality problem. For example, you're watching Netflix. There's your internet connection is not very fast, there's some problem in the line, and then you get some buffering or you get some degradation, the quality. So this is not life critical. No one will probably die in case that your video, or you're playing an online video game, and it has lag, or the ping is not good. So it's good to be within deadlines, but if you're not, it's more of a problem, dissatisfaction on behalf of the consumer, and not a catastrophic event or failure. And real time, I have to emphasize, doesn't mean high performance. Real time means you know exactly the time it should work. And the time could be every 1 minute. Something that responds within a minute may not be fast with today's computers, but this is exactly what we mean real time. We don't mean high performance, but we mean guaranteed timing. As an example of a real-time system, I have here airbag. So an airbag deployment system is real-time because if the airbag deploys after 2 seconds instead of the milliseconds that it has to respond, then it's too late. That the human may have suffered some injury or worst case scenario death in case that the sensor, the computing, whether the airbag should be deployed, and the actuation, the airbag being deployed, doesn't fall within the time that will take that it's needed to protect the passenger. Moving to the OT world, this is again the control loop. We saw there's sensing. The controller is reading the input from the sensor, is computing something, and produces an output that is fed to an actuator, and there's some actuating taking place that is propagating to the process, and the process is changing and produces new values for whatever the sensors are reading, and then you read from the sensors again, and so on and so forth. You have this, as we called in the past, the control loop. So this is, since we're talking about the real world, there are delays in the process, in actually every stage of this of the control loop, starting from the sensors. So when you read, you read a real world value. You read temperature, you read pressure. So when you're reading that, your sensor is reading an analog value, and that has to be converted to a digital value to be processed by the controller. So here, from the sensor to the controller, you have some delay by the time you get the value to convert it to the digital equivalent to be able to process it. So that will take a few microseconds, nanosecond, millisecond, but there is some delay there. So you have delay from the sensor to the controller, and then the controller reads the value and has to compute on it, and that will take some CPU cycles. The operating system is loading the value, is computing by running functions in the controller. There could be system calls, there could be other things the PLC could be doing. So there's some kind of a processing delay within the PLC. And then as soon as the PLC has computed whatever needs to be computed given the input, it has to propagate the value to the actuator. So there's the actuator delay, because the PLC may give a command that, let's say this is a valve, and gives a command that the valve has to go to 60% and to provide 60% of flow. Then it will take some time for the valve to physically move, right? Because we're talking about the real world. This is not an instantaneous action. Actuation will take some time. And by the time actuation takes place and finishes, then we'll see that effect slowly happening into the process. So there's also some propagation delay from the actuation effect to the process itself. How is the process responding to whatever the actuator has done? And to complete the loop and have a full understanding of all the delays, we have from the process to the sensors some sampling delay. So when you try to read a real world value, you don't just read it. You have a sensor that it's sampling over time with some frequency, and then it may do some cleaning up. Maybe something is wrong values, or you need more values. You need to do offset bias, calibration to be able to have the proper digital value or analog value to be converted to digital and go back to the controller. So as you can see in every step of the process here, there is some delay. And when we have a real-time system, let's go back to the airbag, for example. All these delays need to be within some time limit. In the airbag example, it should be within milliseconds, that everything has to happen from the sensor of the crash, like whether the car is involved in a crash, to the controller processing whether it should respond to that or not. It could be a low-speed crash, so maybe the airbag should not be deployed. To the actuator, the actual airbag inflating, and there's no loop in the example of the airbag. There's no actually loop, but there's only sensing, controlling, and actuating. So this has to happen with guarantees. It has to happen within a millisecond, and if it doesn't, the system is useless. So the straightforward way to implement such an architecture is what is called a super loop, as you can see in the slide here. So super loop is what, as the name implies, is a loop that is taking place forever. So you do some initialization, and then you have a forever loop that it reads sensors. So you read the values from the input, you compute on them, you actuate, and then you just wait for the next scan cycle. So if you're doing that every 10 milliseconds, then you just wait for 10 milliseconds, whatever time unit you have defined in your program, and then you start again, read, compute, actuate. You wait, read, compute, actuate. So this is a very straightforward architecture, and on the good side, it's very simple and easy to implement and straightforward, and it's portable. So you can, if you change operating system or if you change your hardware, the same principles apply. You read, you compute, you actuate, and then you wait for your cycle to be completed. On the negative side, there are no timing guarantees, because these delays, for example, reading the sensor or computing, you may have an average execution time, for example, let's say 3 milliseconds to read from the sensor, but there's a chance it will take 3.5 milliseconds or 2 or 6. Same with the compute and the actuate. The only thing that's more certain is the waiting period. So if this takes, let's say, once 15 milliseconds, so one time the loop will take a total of 15, 5 plus 10. Or if that now next iteration takes 2 milliseconds, then the whole iteration will be 12, 10 plus 2. And then maybe it will take 7 the next time. So you see your loops are not timed properly. Once they're 15, the next one they're 12, the next one they're 17. So there are no timing guarantees in place, which is not a good thing, unless you have a huge buffer and you can actually afford that. Another thing that's maybe not as critical in the ICS world, but more in the embedded systems world, this is power inefficient because this wait here is busy wait. So the CPU keeps working by doing nothing. This wait is busy wait. It's just, the CPU is still working, but it's just counting down time in order to escape that time loop to go back to the while loop and start reading, computing, actuating. So the question is, how do you actually enforce timing guarantees? And the answer comes from the use of hardware periodic timers. So the hardware, like a PLC, or even our computers the same, they have some hardware support for precise timing. So you can set up a timer for 10 milliseconds, and within that frame of 10 milliseconds, you do your sensing, computing, actuating. And the timers would be typically coupled with interrupts. An interrupt, as a reminder, is a special hardware signal that triggers a change in execution. So when a timer elapses, the time elapses in the timer, then an interrupt is being triggered at the hardware level, then the system wakes up, it does some action, and then maybe just go back to sleep till a new interrupt will arrive. So interrupt is special hardware signals that allow you to have this precise timing. And the interrupt will not wait for the program to finish. It's unconditional and immediate, and they're very useful for interacting with hardware. So besides the periodicity they offer, there's also a good way to have asynchronous communication. So you don't have to be polling the sensors, do you have a value? Do you have a value? Do you have a value every X time units? But you just wait, and then you get the signal and interrupt from the sensor saying, I have a value, and then you're interrupted, you go back to the sensor, you pick up the value, and you process it. So they're also very useful for interacting with hardware devices. So revisiting the control loop we saw, instead of a super loop, we can have this control loop with interrupts. And let's see what that means. So here you see I have an operation. Let's say X kind of encapsulate everything I want to do, the sense, compute, actuate. So sense, compute, actuate typically takes 10 microseconds in this example. It could take 9, it could take 11, but given my setup, it doesn't make a difference because, as you can see, the way I have set up my control loop, my scan cycle, is that I know I need to be checking the values with a period of 45 microseconds. For every 45 microseconds, I'm checking what's happening with my system, with my control system. And the checking, I've calculated through rigorous measurements that it approximately takes 10 microseconds. And I have the right CPU, I have the right memory, the right hardware to ensure that it is typically around that. But then even if it's 9, if it's 11, even if it takes 20 at one time, it doesn't affect anything because it will finish within the 45 and the processor, the PLC will go to sleep and they'll be woken up by the interrupt to sense, compute, actuate again, go back to sleep, wake up, compute, sense, compute, actuate again, and so on and so forth. So here I have much more precise timing in when I'm reading because I've calculated an upper bound and I talk to my control engineer and they say, you have to be scanning the inputs every 45 microseconds. And if you fall within that, you're fine. You can do 10, 9, 17, it's fine. So this is the alternative to the super loop. That's timing guarantee is there, but then you need hardware support and you need interrupts to be properly set up to support this kind of a scheme. And when we're talking about the operation technology environment, we don't typically have one input. Typically, we have many of these X processes, and a PLC would have many inputs and many outputs. As an example in this slide, you may have a system that has, it reads the infrared, has an accelerometer, has a microphone, camera, IR, and each one of these inputs has to be sampled with different frequencies. Maybe some of them in the order of hertz, some of them in the order of kilohertz, some of them in the order of megahertz. So it's not only that you have to do many of them, you have to do them also in different frequencies. Some of them faster, some of them you have to sample them slower. At the same time, you have ancillary things like communication, Bluetooth, RS-232, that you interface with the external world, and you're also producing your actuation, your output, from producing an LED output to sound from a speaker, or if you have some kind of a motor to move, then that's another example of an output. So now it's becoming a bit more complicated. So you have to both make sure that all of them run at the proper frequency and at the proper time, and the real-time requirements are not violated. So if I expand this to our familiar now sense, process, compute, actuation cycle. So as you said, accelerometer in the example crash detection, right? If in the case of maybe you have a drone that you're trying to understand whether there's a crash or not, or maybe go back to the airbag. This has to happen, this cycle, every 5 milliseconds. The IR is not as critical, so maybe the IR can be done within 10 millisecond period, and the camera itself, because also the camera is a bit slower, the processing and the object recognition can be done every 300 milliseconds. So here you have your sensing, your processing, your actuating, and there's dependency between the different parts. The wheel motors need to be updated by the camera and the AR sensors, and there's a maximum delay you can afford. So now it's becoming a bit more complicated. The super loop was easy. Here, this is more tricky on how to actually schedule this. So you need to schedule in a way how you're actually going to do these X processes. Here, the scheduling in the slide, you read the essential function all the time, like the accelerometer, crash detection, and the LEDs, because remember, the one you have to sample faster more than the rest will be the crash detection one with the accelerometer. And then in your spare time, you can schedule the others in some sequence that you have to make sure that over all the time, the periods of the different tasks, you ensure that they happen either the 10 millisecond range or the 300 millisecond range in the case of the camera with the object recognition. So now, again, this is becoming more and more complicated for the programmer to be able to do properly. So up till now, we have collected so many things that we need to do. We have to handle interrupts, the hardware interrupts that allow us to have hardware interfacing and periodicity in our sampling. There's scheduling that we need to handle and ensure that scheduling is appropriate. And then resource sharing, you have maybe your DMA controllers, your memory. So you have to ensure that when the tasks are being reading from different parts of the hardware, that there's proper resource management, that there's no contention and locked and deadlocks in case of someone getting some resource and the other task is trying to get the same one and cannot. And maybe there's a deadlock that appears. So this is too many things to handle, right? And the solution to that, may be obvious by now, is to employ an operating system. So in a way, the operating system is actually doing all this dirty laundry for you. So instead of the programmer trying to do everything by themselves when they have a system, the OS is interfacing between the hardware and the user application. So instead of you doing all the low-level stuff, you have something that handles the interrupts, handles the hardware, handles the resource management, and you only call a function. So when you want to read from a sensor, there's a read sensor function that does all the things behind the scenes without the programmer being aware or responsible or having to worry about the correctness or how to actually interface with the lowest level of the system. And an operating system typically can be decomposed in the following entities. The scheduler is what we discussed before. How is the CPU being shared for the different tasks? Because one CPU can run one task, and by sequence different tasks in order, we get the illusion of multitasking in case of a non-multi-core CPU. So the scheduler is scheduling how the CPU will execute the tasks. And then another thing of the OS is the device drivers. How do I connect to my USB device in computer, to my keyboard, to my camera, to my microphone, to my fingerprint sensor, to my touchpad? So the device drivers are low-level programs that manage the various devices. In our case, sensor and actuators will have their own device drivers that at the high level, I will get the only the high-level information I need. What is the value from the sensor, and how do I send the value to the actuator? And two more things that are not so relevant in the OT world is memory management. Virtual memory may not exist in the OT world because there's no multi-user environment. So there's no need for virtual memory. And same thing with graphical user interfaces. You don't need a GUI at the OS level. You may have your HMIs, but that's at the software level. It's different, and you typically create it through connections to the PLC. So an operating system is handling everything the programmer should not be handling, right? So you take Linux and you build on Linux. You don't have to recreate Linux to be able to run something on your PLC. And then we have real-time OS. So a real-time OS is an operating system that has the extra property that is dedicated to meet timing constraints. So it's exactly what an operating system does, but it gives you also guarantees about the timing of execution of the tasks. And the design requirements are a bit different now here. So the response of the OS has to be predictable and deterministic. you cannot be getting different responses every time you run the same task. You have to know exactly how the system responds. Second, it has to be responsive and it has to be properly controlled by the user. So you have to do the right thing fast enough. Fast enough doesn't mean fast, right? It doesn't mean that, I need to respond within nanoseconds. You may respond within a minute. As long as your design, your system can afford that you sample every minute, it's okay if your system, your operating system, has an upper bound of 1 minute. So again, don't confuse high performance to real time. So fast enough means within the constraints that the process engineer has set for the actual process. Fail safety, when something goes wrong, you can't just produce a blue screen and die. You may need another mechanism for graceful degradation of the system and make sure that everything shuts down in a safe for humans way. Example, real-time operating systems, sometimes just custom, they're built by the vendors, and there's some ones that are open, or you get a license, FreeRTOS, Micrium, Windows, VxWorks, Nucleus, and Linux has a preempt patch that enables, that kind of transforms Linux to a real-time operating system by making sure that the kernel functions are preemptible. So in the non-real-time version of Linux, you cannot preempt the kernel functions. But in the RT1, the real-time patch, all the kernel functions are preemptible, so you can have the timing guarantees. And also, the patch itself is promising lack of unbounded latencies. So when you start a function, it will finish within some bounds. And if that doesn't, that's a bug. It's being treated as a bug by the designers of the operating system, and they try to fix it to make sure that every kernel function has bounded latency. So to conclude that part, we've been seeing some kind of transition to more open source real-time operating systems that are taking over the older monolithic firmware approach. For example, in one of our research papers, we identified that many of the Codesys PLCs that you can see on the internet, they use Linux. 33% are using Linux. And there's a good reason for using a real-time operating system that's open source, because you get all these features for free. You can have FTP server, you can have SSH, you can have all the encryption coming from OpenSSL, or you can have your server features, Apache, and so on and so forth. So you don't have to develop how to set up a web server. You don't have to develop how to have an FTP server. You can provide these features to your users by importing the open source packages that Linux has. And at the same time, you have regular updates. The Linux kernel is getting patched for performance and for security, even though, again, the frequency of updating may be trickier for operating technology systems.